let's start our session. So this time Sarah has discussed two things. One is the final thermodynamic part, where we compared how the temperature or how the equilibrium temperature, whether it is solidus or liquidus line, how does it change with the nanoparticle diameter or the size of the nanoparticle. So they have three things that I have discussed in previous class. One is one is the temperature dependence or the equilibrium temperature dependence on the size of the particle, and the second point is how I have derived few things, and in that few things I have also discussed the Joule-Thomson one. So what is the excess pressure, and the third was how the equilibrium vacancy changes with the curvature, or I can say proportional to function of kappa, the curvature, right? So we know here for equilibrium temperature, like for pure metal, when the equilibrium melting point, so because if you're talking about pure metal, then we have only the single melting point. So yeah, we had one axis as R, another axis as temperature. So when I decrease the size of the particle, the temperature also got reduced, right? So this is our decrease in size, so our melting point also decreases. This is what we have proved. I should say, I can write it like this. Instead of writing R, I can write one there. So instead of writing R, I can write 1 by R. So the equation should look like this. Or we got a parabola, right? Or hyperbola type function, where the temperature or the equilibrium temperature got reduced, and the second relation we got is the excess pressure, from which we have arrived, which is 2 gamma by R, where gamma is the surface energy, right? Gamma is the surface energy. And the third one was how the mole fraction of vacancies changes with curvature, and there I have proved we have concave and we had a convex. So this was our convex and this was our concave. So how the equilibrium vacancy concentration changed. Suppose I have a powder particle, both are touching each other. So at this surface, this is a concave surface, so there are more number of vacancies, and more vacancies moves this side, and because actually atoms, how they move based on the substitution diffusion. And how the substitution diffusion happens? The substitution diffusion happens because of the vacancies. So if a vacancies moves in this direction, then the atoms will move in this direction. So this is how we have a room temperature symmetry of powder nanoparticles. at room temperature. So from this we can say if you have a concave surface, then you have more number of vacancies when compared to flat surface. And if you have convex surface, then we have less number of vacancies when compared to flat surface. So this is our final relation. And so finally, this is our last part in dealing with the thermodynamics. So what exactly happening here is how decreasing the size of the particle is going to affect our this is our solidus temperature, this is our liquidus temperature, or should I say the equilibrium, not this one, not the yellow one, this blue dotted line. A blue dotted line represents the bulk, okay, for the bulk of the phase diagram. So this is our liquidus temperature and this is our solidus temperature, XL, XS. So how these temperatures or the equilibrium temperatures is going to change with respect to the size of the nanoparticle. So let's see how they're going to change. Let's assume that I have a phase and there is a formation of a small particle. If we are talking about let's say a small phase is forming next, so then let's take, we have a G, or the free energy of the old component and the free energy of the new component. Yeah, the free energy of the old component and the free energy of the new component. Now what is happening at equilibrium? When two phases are equilibrium, we know even from the the free energy versus composition diagram, even the free energy versus temperature diagram, whatever we try to do, we arrive at one simple condition, that is the free energy of both the phases are equal when we are at the equilibrium. So it should be like G old equals to G new. Now let's derive our equation. Let's go like this. Let's say the G old, we know from Gibbs free energy equation, G old will be enthalpy minus T equilibrium temperature or T transition temperature, T times TR transition temperature times entropy of the system. Next we have free energy mu, that will be equals to the H mu minus TTR S. Now why I am again deriving this equation, because this will help you in solving those the assignment problems, so that you don't have to just by heart those formulas. If you're not understanding anything, you just derive from the basic scratch. So that's why I'm deriving it again, and it's also helpful in knowing what exactly is happening in the derivation, what are the assumptions that we are taking. Now this is for only the bulk components. Now what if we have the nanoparticles, what if the surface properties are dominating, then what should we do? Then it should be like G old equals to G old will be equals to H old minus T transition temperature S old, and G mu should be equals to H mu minus T transition temperature times S mu plus surface energy times the new area that is formed minus old times old, the area that is being lost and the surface free energy that has been lost. So now when two phases are equilibrium, we had an equation G old equals to G mu. Then what is the change in free energy? The delta G transition should be equal to G over minus G mu equals to 0, right? Okay, let's substitute these terms. Let's say this is the equation 1. Take it as the equation 2. Here the new area and the old area, these are both will be equal, because the amount of being lost is equal to amount being generated. Then plus a mu gamma nu plus a old gamma out. Now this will turn into, this is not a minus, so it should be the minus sign. Okay. There should be the minus sign. And this will turn out to be delta G transition equals to delta H transition minus delta S trans, that should be equal to plus gamma nu a nu minus gamma old a old. That's it. Now how we are going to define the areas. Let's say we know the area and volume relation. Let's say for a spherical particle, let's assume that we are dealing with a spherical particle. So for a sphere, the area by volume, right? So let's say for a sphere, we can derive for other geometries, but for simplicity, let's take for a sphere. A sphere has area 4 pi r square and volume is 4 by 3 and r cube. Then area by volume will be 4 by r square times divided by 4 by 3 by r cube. 4, 4, 5 by gets cancelled. Then we have r square will cancel. Then we have 3 by r. Or we can write it as r is equal to 2 times of the, sorry, diameter is 2 times of r, then r will be d times 2. So d divided by 2, then it should be 6 by d. Times d. And we had relation 6 by d equals to b. Now what is volume? Volume again has a relation. Volume equals to mass by density. If you are talking about molecular weight, then it should be the molar volume, and it should be molecular weight, or we can write as molecular weight. Molecular weight by density. Then molecular weight of gold by density of gold. A mu will be equals to 6 by d molecular weight of mu by density of the diameter. So then substituting these two in the previous equation, this one delta G transition will be equals to delta H trans minus T T trans delta H trans will be T trans times delta S transition plus now A nu. A nu will be substituted by, let's write first the surface energy gamma nu times 6 by d times molecular weight of mu divided by density of mu minus gamma old 6 by d molecular weight of old by density of gold, right? Or we can write here mu and old. Then again we can again get the relation between the density and the diameter, and we're just assuming the conservation of mass assumption. In conservation of mass, we assume the mass will remain same even before and after reaction or any type of variant. So let's write it as m. M will be, again we are assuming a spherical particle, so its volume will be 4 by 3 by r cube, or I can represent it as a mu times density of mu, which is again equals to 4 by 3 by r whole cube density of, so it's density, so diameter is density of n or density of mu, density of 4. Now we have a relation to these two gets cancelled. R mu by R whole equals to density of gold divided by density of mu whole power 1 by 2. And because the radiuses are in cubed power, so the densities will be turned out to be density of gold by density of mu whole 1 by 3. And if you want to write it in diameters, diameter of mu by diameter of gold will be equals to density of gold by density of 1 by 3. Now substituting, I should substitute this equation. Then let's write this equation again. Delta G delta G transition will be equal to tr minus t transformation times t transformations times t tr minus delta is tr plus we had a, sorry, we shouldn't write a now because we substituted those terms, so it should turn out to be gamma n times, let's write it, d6 d, or I should write dn times 6 molecular weight of mu divided by density of n minus gamma old divided by d old 6 times molecular weight of old by density of old. Now, if we substitute these things here, then this will turn out to be, if I take out dn, yeah, let's take out common of dn and rho n. Let's see what happens. Let's write this delta g dr equals to delta h dr minus d dr times delta s dr plus now if I take common of delta, what is this one? Yeah, d mu and rho nu, d mu and rho nu. This should turn out to be, and also other constants like yeah, we can take gamma nu as a common, or even if you don't take, if I just put it like this, gamma nu, this will turn out to be, sorry, this should turn out to be r, if I write in radius terms, should turn out to be r old, if I take gamma nu as a common, then this should turn out to be, then here there will be no gamma, 1 minus the radius old divided to the surface strain energy, should I say, the surface strain old times surface strain energy mu multiplied by density of mu density of whole power 2 I think. After taking things in common, then as this should be equals to 0, because we know the delta G transition for G mu, G old equal, both are equal, then it should turn out to be 0. So after substitution we had T trans will turn out to be delta HTR by delta STR minus 6m. I I didn't mention the 6m term, right? We can write the 6m term here. And another thing, I have gamma nu equals to rho nu d nu diameter u times delta s transition into 1 minus old by new intensity, the density of old density of comes to 1. And now another assumption to make our life simpler. We assume this whole term will be beta. Now again, let me add few more slides. What is our change in transition? What is the delta t? How much we are seeing the change? To quantify it, we represent T bulk or T old minus T trans, right? The transition temperature, the current transition temperature, and that will turn out to be, and upon doing the simple calculation, we have T trans and we have T bulk. Then doing subtraction will turn out to be 6 m, because the T bulk, which is equal to delta T transition by delta S trans. So this is this, and in T transition we have the first term, this guy, so this one and this one gets cancelled. So we have 6m times radius of surface energy. Let me write it here. Surface energy mu divided by rho mu times diameter mu into delta S trans times 1 minus beta, and we know what is beta. Beta is gamma old divided by gamma mu times density of mu by density of old, which is 1 to 2. And because of these values, and we also said beta is very much less compared. Well, I should write it like this. Beta is less than 1. What happens? So we can assume beta is very approximately equals to 0, and this term will go out. So what we have, delta T trans equals to 6m gamma n divided by n dn times delta transition. So from that we can draw our conclusion that with this is our temperature graph. This is what I'm going to show you this. Let's say if I just mention R, then what happens? So it shouldn't be 1 by R. So the temperature will look like this. And the experimental point where previously people had done before, so they found out they follows a straight line, or the straight line term. how the equilibrium temperature or the transition temperature changes with R. This is our profile. I will just go back to it again. So it's rather a simple thermodynamical derivation. So we first assume that if we have two phases, we get G over T equals to G mu, and from then we had the Gibbs energy equation. Then we added the extra surface energy part because we are not dealing with bulk anymore. So here is the extra surface energy part, and then from there we derive the area to the area relation to the diameter and the density. So here is our the density and the diameter relation. Then we substitute there, and we have few assumptions where we assume that beta is equal to 51 because of its values. So finally we arrive to this linear equation from which we can see how the equilibrium or the T transition temperature changes with R. Now let's move on to the synthesis part, because so far we have discussed so many things, from the characterization of nanomaterials, not basically the characterization, how we define our nanoparticles. And I will just brush it up again. So how do we define nanomaterials? We characterize nanomaterials in 4 parts. We have 0-dimensional, 1-dimensional, 2-dimensional, 3-dimensional. And how do we define the 0-dimensional materials? These dimensional nanomaterials. So if we are saying the 1-dimensional nanomaterials, then that means 1 dimension is not in nanoscale. So if we are talking about 0-dimensional nanomaterials, where all the dimensions are not in nanoscales, and if we are talking about 1-dimensional nanomaterial, which doesn't have 1 dimension in nanoscale, and again same goes for the 2-dimensional nanomaterials, where 2 dimensions are not in nanoscale, and 3-dimensional nanomaterials, where the 3 dimensions are not in nanoscale. Again, the 3-dimensional nanomaterials have the properties. It's like if you have a whole matrix, let's say I have an alloy, like aluminum copper, and inside my matrix I have nanocrystals. That will be called as 3-dimensional nanomaterials. And the same goes for film deposition. For example, if I have a substrate, a very big substrate, which is 3-dimensional material, not nanomaterial, which is a 3-dimensional material, because it has a 3 visible dimensions, like that. And no one dimension is in nanoscale. Then what happens? What after that? I deposit a thin film on its surface, then our thin film is in nanoscale. So again, it will turn out to be 3-dimensional nanomaterial. So, and this part we have the synthesis part. In the synthesis part, I'm not going to discuss every point, but I'm going to discuss only the important points that will help you in solving assignments. And if you miss doing your assignment, so let's start. Let begins with the inert gas condensation. So I will progressively start from 0 how do we synthesize the 0-dimensional nanomaterial, then 1 dimension, then 2 dimension. So whenever I change the synthesis part, I will tell before that this is used for production of this type of nanomaterial. Okay, so far so good. This setup is used for inert gas condensation. Now, let me write it. Inert gas condensation, right? So I have 3 terms: inert gas condensation. Right? So inert means inert atmosphere. The whole atmosphere is very inert. There is no chemical reaction happening in it. And second one is gas. So we are using gas molecules. And the third one is the condensation. Now, what is condensation? Condensation is a transformation of the phase from vapor to solid. Right? So we are condensing a medium. It can be either from solid to liquid or solid to gas. Condensing is nothing but making the molecules come very closer. So we define two condensed systems. We have two condensed systems. One is liquid, another is solid. And gas is a non-condensed state because solids and liquids have like very comparable volumetric ratios, so molar volumes. So I shouldn't say comparable, but there is a resemblance. There should, again, no resemblance, but the values are very much like, for example, if I take the molar volume of some solid and if I take molar volume of some gas, there is a drastic change, or there is a big difference in between the values. But when I again compare it to liquid, there is not much difference, right? So yeah, there might be change in few values, like from 10 like 1 order, right? So this is the how. So I'm going to tell about the inert gas condensation. So I have explained 3 terms. Now, what is happening? So I have my heating source. Right, I have my heating source here. This is my heating source. So this is my heating source, or I can call it as a boat, where in boat I keep my materials and then heat the boat so that the material gets evaporated. So what type of materials we are using inorganic materials, right? Because inorganic materials have high vapor pressure. They just evaporate on a very nominal temperature like 400, 500. But the same can't be true for metals. For example, iron, it has a 1.5 like 36 degrees centigrade. So that is very much high compared to inorganic materials. So in inert gas condensation, we mostly use the inorganic materials, which has nominal melting temperatures, not very high melting temperatures, right? So again, now first what we do is we have a tray or we have a boat and we have material here. What we do is we heat it. For heating, the gas molecules will won't condense, they will evaporate, and we have vapor molecules. These molecules will be carried out by this gas, and this gas is an inert gas. So vapor molecules are taken by inert gas and they travel away from the train or away from the boat or the heating filament source. Right? So in between, so after traveling, they came near to the zone which is known as cold zone. We have a special thing which is called as cold finger. Cold finger is nothing but the cold surface where we pass the coolants, and the coolants here are the liquid nitrogen. To cool it very fast, we use liquid nitrogen. So liquid nitrogen has minus 167. So it should be near to less than 160. So these molecules, what they do, they coalesce at the surface. 2 molecules coalesce together and form a large molecule. Right? And these molecules are collected at the bottom. So we have a vacuum pump which takes out the molecules that are deposited. I shouldn't say deposit, but which are collected at the cold finger. So these agglomerated, these coalesced particles will be collected down in collection cup. So what type of materials we used? We used inorganic materials mostly. Inorganic materials. Now we can even use the heating sources like we can have a sputtering target instead of just a muffle furnace, or we can even have the laser ablation, and we can even use laser to heat up the material and evaporate the particles. The next question: what is the condensation? The next question is the type of gas that we use, the type of inert atmosphere we provide, right? Type of inert atmosphere we use argon or xenon gas. We use argon gas mostly. Next, the type of coolant. We have liquid nitrogen, we have simply water, the other coolants. And there is a difficulty in controlling of the process parameters because we can't avoid the coalescence of the nanoparticles here. We can't avoid the coalescence of the nanoparticles. So there is very poor controlling the functionality of the nanoparticles, and because there is a clustering, the nanoparticles may form clusters. So need for controlling of process parameters. This is the bottom of approach. Why? Because we are evaporating the atoms, then we are coalescing them to form the nanoparticle. So it is a bottom up approach because we are coming from atoms, right? So this is one of the bottom up approach. Then again the process which is same as the inert gas condensation. This process is inert gas expansion. So what is the difference between these two processes? What is the difference between them? Again, the process is same. The process is same, but the only difference is instead of condensation, we have evaporation. Same, because the process is inert gas evaporation. So again the same. We have the nanoparticle, we have the material which needs to be evaporated, which is an inorganic material. Inorganic material which is ready to evaporate. We first heat the inorganic material, then we have a vapor. This vapor is traveled through orifice, and this is my orifice, or I can say it is a small gap from which I am evaporating, from which I am passing my vapor or the inorganic vapor. What happens? So upon expansion, write it clearly, upon expansion the vapor it's cool. And because of that, sorry, it's cool. Yeah. And because of that, we have coalescence, and we have nanoparticles. Because any type of heating source, same as I have said in before, we have laser melting of surface, we have sputtering type, where we bombard the surface to eject the atoms, and the normal or the conventional one, which is the heating of the material to reach the vapor phase. So these are the things. We can use different types of heating systems. When we have a laser melting or laser cladding, you can call it as. Then you have sputtering, where we sputter the surface, which is nothing but the bombarding the surface with ions to eject the atoms from the surface. The conventional one, which we have represented here, is the heating of the material. Again, the same drawbacks. The nanoparticles may cluster because there is no control. There is more control in this process when compared to the previous process, because in first process we are condensing. There is a fixed room or fixed volume, but when compared to expansion, where we are trying to increase the volume, it has a less tendency to coalesce. So if we control the process parameters, again, we control the process parameters, we can control the coalescence. The coalescence of nanoparticles. So these two, this one is the inert gas condensation, this one is inert gas evaporation. Again, this is also a bottom up approach, because we are again melting the material. We are having a vapor of atoms, and then we coalesce them to form nanoparticles. And the third process, which is called as the sonochemical process. Again, here there is no direct coupling between the chemical species, but what is happening is just the sound waves that are produced at high frequency when compared to conventional sound waves. So that is the sonochemical process. What exactly is happening here? So sound waves are nothing but waves. Right? We have crest and we have trough, and the sound waves are represented as a pressure difference. So delta P, the pressure difference will be oscillating around a mean position. We have high pressure, we have low pressure, so there is a pressure variation or the pressure oscillation in sonochemical process. So actually the conventional sounds produce the difference in pressures at a certain point. That's how the sound travels in a medium, by creating oscillating pressure differences, right? So there are different types of sources that we can use to produce sound waves. One is the magnetostrictic properties, where we apply magnetic field that will produce magnetostrictic. I will write it as a MS. If we have a material, if you apply the magnetic field, let's say I apply magnetic field in this direction, then what happens? It produces a displacement because of the spins or because of the domains aligning accordingly. So there is a displacement, or there is a stretching or compression of the material. One, that is the magnetostrictic, or we can use as a piezoelectric materials, where we apply electric field. We again stretch or contact depending upon the amount of electric field that we are applying. So there are two things. One is application of some force, or some application of some other external agency, and then we have a response, right? So the response depending upon what is the force or what is the type of external agents that is being applied on the material. Response. So let me have one more slide. See, this is our sound that is traveling in a medium. Let's say delta P. Just I have mentioned before, the sound travels as a change in pressure. Because if we do not have any changes in pressure, then the system will remain at equilibrium, so the sound cannot travel. So the same thing happening here is the change in pressure, right? So this is how it oscillates with respect to distance about the mean position. We have, let's say this is our compression, right? These all parts, let's say these all parts represent of compression, right? Like these, for example, see, this is the compression of air molecules, is the expansion of air molecules. So if I represent in wave diagram, it should look like this. This is my compression part and this is my expansion part, or even I should say the stretching. One is the compression and another one is I have a molecules or the chemical species. Now what I'm going to do is I'm going to tune the sound waves into the medium. Now what the sound waves are going to do? So in the compression part, the sound waves compress the chemical species, and in expansion and in stretching part, it stretches the chemical species. So what happens in stretching? Stretching, and because of stretching of atomic atoms in the medium, there is a gap or the excess volume that is created, and this excess volume creates voids, or you can call it as bubbles. If we have air that is dissolved in our medium, then in stretching of liquid molecules will create the air popping, just like, for example, let's say I have a medium and I'm trying to stretch. So these are my, let's say how this is my medium and this is my imaginary line from which I'm stretching. I'm applying forces on both sides, and suppose I have a gas dissolved in it. For example, let's say I have a material and I have a helium, for example, or you can say it as a nitrogen, which is dissolved. Let's talk about the inert gases. There is no reaction involved in it. So we know from Raoult's law, every liquid tries to attain a certain vapor pressure or certain dissolution of air molecules inside the medium. It depends on the pressure, right? If we have a saturation vapor pressure, then depending upon that saturation vapor pressure, we have some more fraction of atoms dissolved in our liquid. So what about if we create a vacuum? Again, the least ideal principle. The system tries to attain the equilibrium. Right? So to attain equilibrium, the system tries to spit away the air molecules that dissolve in the system. So the same thing that is happening, right? So in stretching, there is a formation of a gap, a void, which is a small vacuum. You can call it a vacuum drop. So this vacuum drop this vacuum drop try to take away the molecules or the air molecules that are dissolved in a liquid medium. Now, this is our the stretching cycle. Now, what happens in compression cycle? So, once these air molecules are formed or the bubbles are formed, the compression part tries to compress these bubbles, right? Again, the pressure increases. So, the next cycle, which is again stretching, and because of stretching, we again have some the droplets also, not the droplets, but the bubbles that are being created. And in the next cycle, these some bubbles may get destroyed and some bubbles may coalesce, right? If you have two bubbles very near to each other, in the compression cycle, they try to coalesce and form one single bubble. And with increasing the size of the bubble, it is equally likely difficult to destroy the higher the size of the bubble. So if you have a smaller size of bubbles, it is easy to destroy in compression cycle, but not the same for the high size bubbles. So once the higher size bubble forms, the cavity diameter will go on increasing. Why? Because of coalescence. So once they reach a critical size, they will burst and they create enough amount of energy. To coalesce the material and to form a nanoparticle. And that is how the sonochemical process is used to create a nanoparticles. And the bursting of the cavity, or I can say the bursting of bubble, will create enough amount of energy, and we even call it as a hot spot, or the high pressure trigger reactor, high pressure trigger chain, which triggers the reaction to form or the creation of the nanoparticles. So this burst zone is also called as a hot spot. Now, what is the size that we can create from this sonochemical process? We can create up to 2 nanometers size of nanoparticles, and large volume can be made when compared to previous process, where the inert gas condensation and inert gas expansion with small amount of material with the same amount of material compared to previous process. Again, this process is a bottom-up approach where we have a medium of atoms and we are coalescing these atoms with pressure, or the cavity pressure, which results in formation of nanoparticles. The next process, again, this is a bottom-up approach. So this process is known as a sol gel process. Let me write it. This method is known as sol gel process. What are the things that are involved in it? So first, we have a precursor. A precursor is the solution of nanoparticles that are we are going to make, the species of the nanoparticles, right? So we have a solution which contains precursor, or this precursor we normally use the precursors such as the inorganic metallic salts or metal alcohol salts. Now, the next one is we add some polymerizing agents. We add some polymerizing agents in this precursor solution. precursor solutions has the independent molecules which are not bonded to each other. Now, what the polymerization agent does is to form a polymer of these monomer molecules. Now, this after polymerization, we have a salt, which is a discrete, finely dispersed particle suspended by adding surfactant. Now, this suspension is converted to gel by the chemical treatment, where we do the evaporation or so condensation process. The chemical treatment to disseminate the surfactant to create extended network of connected particles, making superpolymer. Again, I will explain it again. So first we have precursor, which is subjected to polymerization to form a sol, and then this sol is which is a discrete, finely dispersed particles which are suspended by some surfactants so that they don't coalesce. The surfactant forms the micelle so that no two particles get coalesce, and this suspension is converted to gel by a chemical treatment to disable the surfactant to create extended network of connected particles, making the superpolymer. And this enormous molecule or the network is called as a gel. And evaporation of solvent will leave the dense, or which is the dense or sometimes the nanoporous film, because some gas molecules will get trapped. So we have a porous type of material. And also the sol gel methods are a base for paints such as ceramics or cosmetics, coatings and derivatives. So it is again the bottom up approach. Bottom up approach. The next process is the molecular self-assembly process. Now in molecular self-assembly, molecular self assembly. Now what happens in molecular self assembly? In this process there is a self organization, the proposition of molecules, of organic molecules. Right? They organize themselves to form a structure or a compound. Now there are few examples for the self assembly of molecules or self-organization, and first we have the crystallization of sugar. This is one of the type of molecular self-assembly process, and not only sugar but even if we have a salt solution, we try to cool down, when you try to freeze the salt solution, we have the molecular self-assembly of the organization of molecules. And in this, what we do, we create a conditions which makes atoms of molecules to self-assembly, or what? So what is the driving force? The driving force is the minimization of the energy, and to bond like end-to-end bonded by relatively weak bonds. Is the few, if we compare the energies, like the driving force is few orders, like it's like multiplied few times by kT, but the same when it's compared to self-assembly, which is bonded relatively, will have an energy which is just a few times of kT, where K is the Boltzmann constant. Boltzmann constant. T is my temperature. So at first I have K as a Boltzmann constant, T is the temperature. Let's say I have a value of Z, which is a few orders greater than, let's say it is Y, which is few orders greater than Y. That is the energy gap differences between the self-assembly and the reduction in energy. let me give a easy example. So self-assembly molecules. Self-assembly molecules. Self-assembly molecules forms miscellaneous. Miscellaneous groups like this. Also in soap solution we have dirt removal to the miscellaneous formation, right? So we have a surfactant which is a polymer, which is a long chain polymer. It has two parts. One is the hydrophobic part, which is the tail part, and the hydrophilic part, which we call as a head. And what hydrophilic part does is it attracts towards the water droplet. Why water droplet? Water droplet will have the polar bonds, right? H2O. So oxygen is negative, H is positive. So there is a polar bond. Now this polar bond is getting attracted towards the philic part. So the head will get attracted to water droplet, but not the tail part. The tail part is hydrophobic. It tries to avoid the tail part tries to avoid the water droplet, but the head part, which is hydrophilic part, tries to get attracted towards the water droplet. Miscellaneous or amphiphilic molecules have one end soluble in water and the other one is not. So one end soluble in H2O and another end repels H2O. And also we have self aggregates, right, depending upon the concentration of these molecules. And and this center of miscellaneous, right? There is a chain connecting to it, right? Like this. Suppose we have miscellaneous formation, and this center part will act as a reaction zone for some reaction mechanisms. In the next one, which is here we can see, and in miscellaneous we can even form the 2D nanofilms. In cell molecular assembly, we can even form 2D nanofilms. And one famous technique which we use to form 2D nanofilms is Langmuir blot gate. Blot gate technique. Now, what is so there is he's a famous scientist who proposed this technique to form the 2D nanofilms, and he took a fatty acid. He formed this Langmuir blot gate formed a fatty acid monolayer on a water surface, which is a single layer, single atomic layer, or people call fatty acids monolayer. He formed the fatty acid monolayer on a water surface, where the polar part, here we can see, suppose these are the miscellaneous, and this is my fatty acid. So what is happening to form a monolayer of fatty acids, suppose this this polymer, suppose this polymer molecule is my polymer compound, not polymer compound, this monomer compound is my fatty acid. Then what I am going to do, so I have a substrate, right? So what I am going to do, I am going to drag this stuff. Now what happens in a solution containing fatty acids, I drag this substrate. So I drag this substrate out from the solution containing the fatty acids, and because the fatty acids have a hydrophilic and hydrophobic ends, and the hydrophilic end gets attracted to the substrate, and the hydrophobic end moves away from the goes away from the substrate, which shows its head away from the surface. So we have a monolayer of fatty acids that gets attracted to the substrate. That's how the Langmuir blot gate create a 2D nanofilms. And again, this is also a bottom-up approach. Why? Because in fatty, we have fatty acid solution where each monomer is a separate entity, and I am having a substrate. I dip my substrate into the solution, and because my substrate has a property such that the fatty acids hydrophilic end gets attracted towards it, so it gets attached, or the heads get attached, and the tail will be away from the substrate. That's how Langmuir-Broadgate created a monolayer, a fatty acid monolayer. Again, see, this process, the Langmuir-Broadgate or the nanomaterials is a molecular self-assembly process, is used to create this Langmuir-Broadgate process is used to create 2D nanofilms. Right? Now, the next part, again, how to create a 2D nanomaterial. And this is another process to create a 2D nanomaterial, which is the electrodeposition. Let me write it. This is electrodeposition process. This is an electrodeposition process. Now, this is an electrodeposition process. Now, what happens in electrodeposition process? In electrodeposition process, we have a solution. We have an electrode, which is a positive cathode electrode and anode electrode. And to cathode electrode, we have a negative sign, and anode electrode we have a positive sign. We have a metal solution, a metallic, any metal ions or contain any other solution, which contains precursor, which we want to deposit, which material, like we want to deposit copper. For in electrodeposition, I'm talking about the pure metallurgical part, where in refining or extraction, to deposit copper in electrodeposition process, we use a copper solution, right? So we have an electrode, and from copper solution we apply. In copper solution we apply electric field, right? We apply field to the electrodes. We have two electrodes and we have a solution, a copper solution. Now, after applying field, so because the charges accumulated on the electrodes, the solution containing carbon, the ions in the solution, will move towards the respective electrodes, depending upon the charge. Suppose if I have a positive charge, that will move towards the anode, which has a positive terminal, which has a positive charge on it. And if I have a negative ion, that will move towards, if I have a negative ion, that will move towards positive electrode, that is the anode. And if I have a negative ion, and if I have a positive ion, right? If I have a positive ion, that will move towards the negative electrode, right? It's the cathode here. So the same things happen to deposit metal layers on conducting surfaces. And yeah, we need to have a conducting surface, right? So that the electricity can pass and have a charge created on the electrode. So to deposit metal layers on the conducting surface, the solution must contain ion, so that they can move towards the electrodes. So the ions in the solution deposit onto the negatively charged cathode. Suppose if I have a positive ion, that needs to be deposited, right? Suppose I have a metal are mostly the positive ions, positive oxidation states, right? So if I want to deposit this metal, so I have my negatively charged cathode. I have a cathode which is negatively charged, right? Because this is negative terminal, this is positive terminal, this is cathode. Let me write it clearly. This is my cathode, and this is my anode, right? So I have a cathode and an anode. So if I have a positive ions, the positive ions will move towards the cathode and they get deposited. So the rate of deposition is measured, the amount of material that is getting deposited is measured by current in the external circuit. The higher will be the current, the higher will be the deposition, because the higher the charge negative charge we are supplying, so that the metal ions get reduced and deposit will increase, but the supply will more negative charge. Now, controlling the structure is very challenging because once we form or once we nucleate a material, that will start growing. Now we don't want the growth, but because once it starts growing, its dimension will drastically change from nano regime to micro regime. So once we need reach more than 100 nanometers, that material cannot be called as a nanomaterial, right? Because for nanomaterials we should maintain this one dimension to be a nano dimension, right? Because we already had a substrate which is in micrometer, which is not a nanomaterial, and to form a nanofilm, we need at least to form a two-dimensional nanomaterial. We need at least the thin film. We need at least the thickness must be in our nano region, right? For two-dimensional nanomaterials, we have like two-dimensional not in nano dimension, which is length and breadth. What about the height? The height should be in nano region. So to suppress the growth, what people have suggested was to give the pulsating current. See, so first, the most electrode deposits are columnar in nature. The deposition, which is normally happen, for example, see, I have a cathode here, and once the material gets deposited, they start growing like this, and we call this thing as a columnar, or in metallurgy, solidification, we call it as a columnar grains. The same thing happens here. Now, to obstruct this growth, we sometimes add a growth inhibitor. So what does it do? That condenses on a crystal surface during the off stage. Now, the second one is that discourages the continued growth during on stage, and high current density. Now, the other thing was have a high current density. Now, what high current density do? High current density will provide many nucleation sites. There is a burst of nucleation sites, and from that there is a formation of nucleation crystals. See, if you have a high current density, we have many crystal nucleus that are formed. Now, if we give low time, then we have very low time for growth and can provide porosity-free nanocrystalline deposits. And see, in this type of the electrode deposition, we have the porosity-free nanocrystalline deposits, and we can reach thickness up to 5 nanometers. So, by using pulsating current, we can obstruct the growth of the columnar grains, and by supplying the high current density, we can give many nucleation. We can provide nucleation sites so that there is a burst of crystals. Now, if we give limited time, then we have very low growth of the films. And depending upon the current density and depending upon the dwell time, we can control the thickness and growth. We can control the thickness and growth time of these thin films. Now, let's move to and again, this is bottom-up approach. Why? Because again, we are starting from a solution. We have ions get deposited, they form a thin film or a thin film, or we can say or nanomaterial from the ions to nanomaterials. So it is a bottom-up approach. And next, move on to other process, which is the physical vapor deposition and chemical vapor deposition process. And what does these processes mean? See, in physical vapor deposition, we deposit a thin layer of material is deposited from vapor to object. See, and this is our heating segment. We have a heater which heats. Let's say this is a boat which contains our material, and this gets heated. Once it gets heated, it tries to evaporate. Once it gets heated, we have a vapor pressure that is created on the vapor, and this vapor is transported and this vapor is transported so that or this vapor will get deposited because of the thermal gradient, and because the vapors have less density, so they try to move up, and because this chamber is cooled, so this vapor gets deposited on the substrate. So this is known as a physical vapor deposition. And why do we call it a physical vapor deposition? Because we are changing the physical property, right? So property, like physical property, from vapor, from materials condensed phase to vapor phase, and again from vapor phase to condensed phase. And we have different types of, again there are different types of heating zones. Like we have a direct heating in vacuum that condenses out the cold substrate, and we even have a physical vapor deposition ion plating, where vapor is ionized and accelerated by electric field. So how we accelerate? We accelerate by the electric field. Suppose I have a, let's say, the same, the acceleration that we see in the scanning electron microscopes, the transmission electron microscopes. Once the electrons are ejected from a sample, they are getting accelerated. So we have a anode which ejects the electrons, and cathode which the atoms are again collected at some position, they again get deposited there, and we have a nanofilms or nanoparticles. And and use of reactive gas can be used to form compounds. So this is one process which is the physical vapor deposition, and there is another process which is the chemical vapor deposition. In chemical vapor deposition, it is same as physical vapor deposition, but the difference is we have a heater, we have everything, the coolant, everything is same, but instead of just changing the phases like from materials condensed phase to vapor, vapor phase to condensed, we chemically react the species to form another species. Like for example, if we want to deposit like SiO2, silica, what we do, we have a Si and we have oxygen, we try to react it, and then we form SiO2 which gets deposited. I'm just using a normal example, which is not, this process is not used actually, but I'm just giving an example. We have two different reactants, and these reactants react to form a product, and this product will be deposited on the surface. And here reactant gas mixture is brought into contact with surface. Same, the decomposition of reactant gas, sometimes we use a decomposition reactions, like we have, there are different types of reactions. There is a combination reactions, there are decomposition reactions. So we can use any type of chemical reaction to deposit our material, and the reaction between the precursor gases or vapor to surface to form on the surface. And the required there is a requirement of temperature for example, if you have an endothermic process which needs temperature, so in that case we need a temperature. And there are other types of CVDs. There is a plasma enhanced CVDs where we form plasma to melt some materials so that to get the enough temperature for the reaction, which is also called as PECVD, right? PECVD, which is plasma enhanced. Which is plasma enhanced chemical vapor deposition. And or even we can, there is another chemical vapor deposition, that is a laser CVD. And typically we have nanocrystalline or amorphous types of material that can be formed. So please remember this. We can form nanocrystalline and amorphous. Both type of materials can be formed by using this process. Next slide. Yeah. Now let's move. We are moving on to the 3D nanomaterials. This is known as a melt spinning process. It is a type of process to produce 3D nanomaterials. We produce ribbons basically. So we produce nano ribbons. So we have a melt, which is this is at elevated temperatures, and this melt is poured onto a water cooled drum which rotates at high speeds, 1400 rpm, and this decreases the time required for the transformation from solid to liquid, and a jet of liquid melt is squirted onto the spinning water cooled drum, which results in the formation of ribbons or the nanocrystalline ribbons. And if we control the cooling, or how fast the jet is expanding and how fast it is falling, and the temperature of the drum, we can even form the amorphous ribbons. So there are two types of materials that are formed here. One, we have nano crystalline ribbons, right? And the second one is nano, sorry, not nano crystalline, it should be nano amorphous material. Now, and depending, just I mentioned before, just depending upon the temperature or the heat, the cooling rate, we can form glasses. We can form glassy materials, which is the amorphous one. And the next process here, which is the next process. Next process here is the laser surface melting. We have a laser. We focus a very fine beam of laser onto very localized position to melt that localized place. So use laser beam for rapid and focused melting. The surface, the substrate, or we can call it surface. The substrate acts as a heat quench, because what does it do? So see, let me draw it here. We have a top surface and bottom surface. We focus the laser beam onto the top surface, so only the top surface will get smelt, but the bottom surface remains unchanged. But what happens, and because of very localized heating, that surface, that area will get heated rapidly, but the below surface acts as a quench, because it's just like the heat region is touching with the colder region, so heat region will act as a quench. And this process is readily used for the formation, for the making, the synthesis of amorphous silicon for cheap solar cells. Right? The amorphous, this process is used for this process is used for amorphous silicon, right? Spelling is wrong. Then I did again. Amorphous silicon for solar cells. And the most famous process, which was followed, which can we go went back to a few years, like few centuries ago. This process is also known as the foil beating process, where, for example, we have a very, let's say, a few free sheet, for example, few sheet like 2 or 3 sheet. What we do is we just hammer it down, like we just beat it, and we heavily deform it. For example, if this is my thin sheet, and if I constantly beat this surface, or we constantly deform this surface into this direction, right? We are applying stress normal to the surface, so the material will expand in this, right, and it will compress in this direction. So if we continuously go on hammering the surface, we have a very thin layer of form, and this is how we have a gold leaf. Sometimes people used in eating also. Sometimes in some foods, you people have must seen in some foods we use a gold leafing And in some sweets we have some silver lining, right? Silver leaf or the silver layer forming on some sweets. So how do you form? Here's the process we follow. We just heavily deform. We go on beating and beating this surface such that you have very thin layer. And this process has been followed throughout the centuries ago, right? So this process is known as leaf beating. It's a top-down approach because we have a bulk material, right? We have a few range of material, and this material is getting reduced to very fine layer, like few microns. So this is the bottom of so top-down approach formation while suppressing the fracture. So what's going to happen here is the rod is forced to go through a die, forced to go through a die of very smaller size in and emerges of a rod of some diameter but with refined structure. And we can have a grains from 100 to 500 nanometer grains. So what's going to happen is, suppose if I have a structure and if I have a grain, so in once we start deforming, suppose this is my structure, this is the cross section of this material. Suppose if I have a see, let's say I have a die and this is my material. So clearly, yeah. Suppose this is my material of this cross section and I have a die here which reduces the cross section, and I have a material with a less cross section compared to initial one, right? So we have a heavy deformation here in one direction. So this is, let's say this is my cross section, and because of heavy deformation we have a dislocations forming right here, from dislocations forming here in this grain, in this grain, in this grain. So what happens? And if we do the extreme plastic deformation, these dislocations will get entangled. These dislocations will get entangled, and once to decrease the total energy of the system, these dislocations will get arranged in certain fashion. These dislocations will arrange in certain fashion, and which results in formation of small angle grain boundaries. And because of this we have a separate grain boundary. We have very fine grains that are formed, and these fine grains can be ranged from 100 to 500 nanometers grain size. See, this is a process. This is a top-down process where we have a bulk material and we severely plastic deformation and with suppressing fracture so that the material doesn't break. And we have very fine grains from, suppose we have very large grain. From large grain we are going to a nano, from very small grains, so very fine grains, which is ranging from 100, which is a nano resin, to 500 nanometers. So this is a top-down approach. So far I have discussed many processes. The nanomaterial, the extrusion process, which is the equiaxial extrusion, which is the top-down approach. Go to three-dimensional nanomaterials, and again have a leaf beating, again a top-down approach. The melt spinning, laser ablation, and we have a PPD, CVD to create 2D films. Again I have a electrodeposition, which is again 2D film, two-dimensional nanomaterials, which is 2D nanofilm for synthesis process. And I have lamellar blood gate, which creates again a layer of a monolayer of fatty acids, and I have self-molecular assembly 2D, and again I have a soldier process which again creates the 2D nanomaterials, and the sonochemical process which creates nanoparticles. I have inert gas condensation, inert gas extraction. So these are the different processes, and before I have discussed the thermodynamics part. So with this I'll end this session 7. So thank you.